Today we are going to discuss about Euler's theorem. To find Euler's theorem, we have to know that what is functional, what is variation, what is admissible curve, in earlier class we already discussed about what is functional, what is variation, and what is admissible curve. Today we are going to discuss about Euler's theorem in detail. First we see what is the statement of Euler's theorem here. Euler's theorem statement: let the functional be gamma of y of x is equal to integral x naught to x1 f of x comma y dash of x into dx be the basis of y of x naught, be the basis of y of x naught. Y of x naught is equal to y naught and y of x1 is equal to y1, and all the bounded points of the admissible curves, to then find the extreme, maximum or minimum of the given function. First we see what is the overview of the given statement of Euler's theorem. That is here only given that only the statement, and we only know that only one function, that is gamma of y of x is equal to integral x naught to x1 f of x comma y of x comma y dash of x into dx. By using these functional, we have to find the extremum. We have to find the extremum of the given functional. That is, what is extremum here? We have to find which is maximum or minimum of the given functional. Only by using these functional. So first we see the what is First we see what is the overview of the Euler's statement, how we are going to solve this Euler's theorem. So we have the functional gamma of y of x is equal to integral x naught to x1 f of x comma y of x comma y dash of x into dx. Say it as some equation. Therefore we also know that by the definition of functional, the equation 1, that is mu of y of x is equal to integral x naught to x1 f of x comma y of x comma y dash of x into dx is defined on the curve y is equal to y of x. Y is equal to y of x. Y is equal to y of x. Therefore, by using the equation 1, that is the functional gamma of y of x is equal to integral x naught to x1 f of x comma y of x comma y dash of x into dx. Now we have for this equation we have to equate to 0. In this function, in this statement, in the statement of Euler's theorem, in the statement of Euler's theorem, we know nothing. What we have to find we have to find the extremum of the extremum which is maximum or minimum of the given function. So we have by using equation 1 we have to find maximum or minimum. That is first we equate to 0 in equation 1. Equation 1. For this we need a admissible curve. What is admissible curve? For this we need a admissible curve. Admissible curve. Which admissible curve means the curve which is closely lying. The curve which lies close to the main curve. That is y is equal to y of x. Y is equal to y of x. Therefore, the admissible curve can be written as y is equal to y bar of x. Therefore, we have two curves, that is y is equal to y of x and y is equal to y bar of x. Therefore, taking these two into one parameter. Taking these into one parameter, therefore we need family of curves. Therefore we need family of curves. Therefore we need family of curves. How we can represent family of curves? How we can represent family of curves? We need a family of curves, that is y of x comma alpha. Y of x comma alpha is equal to y of x plus alpha into y bar of x minus y of x. Alpha into y bar of x minus y of x. Therefore where it can be written as, if alpha is equal to 0, then if alpha substitute alpha is equal to 0 in the place of alpha is equal to 0, then the equation 1 becomes y of x is equal to y of x. Y of x is equal to y of x. If alpha is equal to 1, substituting alpha is equal to 1 in this equation, in the family of curves, therefore here we get that y of x comma alpha is equal to y of x plus alpha, substituting alpha is equal to 1. Therefore substituting alpha is equal to 1. Therefore here we get that y bar of x minus y of x. Therefore y of x plus y of x minus y of x get cancelled. Therefore here we get that the y of x comma alpha is equal to y bar of x. That is, alpha is equal to 1. Therefore y of x is equal to y bar of x. Therefore satisfying. Therefore here the family of curves. Therefore here the family of curves. Therefore here family of the curves is satisfying the given condition. Therefore y of x comma alpha is a family of a curve. Now here in the family of curves, y of x comma alpha is equal to y of x plus alpha into y bar of x minus y of x. Therefore here we take the variation. That is, here we take the variation. We already discussed the variation in the previous lecture. Therefore the variation here, delta y is equal to y bar of x minus y of x. Therefore substituting these variation in the family of curve. Therefore here we get that y of x comma alpha is equal to y of x plus alpha into delta y. Since delta y is equal to y bar of x minus y of x. Therefore here, by using equation 3 in equation 1. Therefore here implies gamma of y of x comma alpha. Is equal to pi of alpha. Where pi of alpha is extremized for alpha is equal to 0. Therefore the derivative of the function pi dash of alpha is equal to 0. Now pi dash of alpha is equal to 0. Now next step. Therefore equation 1 becomes, that implies gamma of y of x comma alpha is equal to integral x naught to x1 f of x comma y of x comma alpha y dash of x comma alpha into dx is equal to pi of alpha. Therefore here we get that pi of alpha is equal to, we know that gamma of y of x comma alpha is equal to, gamma of gamma of y of x comma alpha is equal to pi dash pi of alpha. Therefore pi of alpha is equal to integral x naught to x1 f of x comma y of x comma alpha and y dash of x comma alpha into dx is equal. We see in detail, that is what is the statement here. Let the functional be gamma of y of x is equal to integral x naught to x1 f of x comma y of x comma y dash of x into dx, y dash into dx. Therefore be the basis of y of x naught is equal to y naught and y of x1 is equal to y1, all the bounded points of the admissible curves. And then we have to find the extremum of the given functional maximum or minimum of the given function. Therefore now let me see the proof. By the statement of Euler's theorem, given that y of x naught is equal to y naught and y of x1 is equal to y1. Therefore that is by graphically by graphically we can represent it as x-axis and it has y-axis, x-axis and y-axis. Therefore the point, say it has a point x0 and it has a point x1. Say it has a point, it has a b point, it has a point, and mark this as. Therefore here we get that therefore y of x naught is equal to y naught, that is equal to point A, and y of x1 is equal to y1, that is point B. Therefore by the given statement is satisfying the given condition. Therefore now let the functional, now we see the later theorem. Now let the functional be f of x comma y dash be 3 times differentiable. What it means f of x comma y dash be 3 times differentiable, that is a function f of x comma y dash be 3 times differentiable means it's first order, it's first, second and third partial derivatives exist and are finite across in its domain, allowing up to 3 level of differentiation with respect to its variable, variables, that is x comma that is x with respect and x with respect to y, and y dash is equal to dy by dx. Therefore we already know that a necessary condition for an extremum is that the variation of the functional that vanishes. Vanishes. We later discuss in the upcoming proofs. Therefore now assume that the extremum is attained on a twice differentiable curve y is equal to y of x. Therefore since we know that the given function is attained attained or defined in a curve y is equal to y of x, Therefore we know, since earlier we discussed that the curve gamma of y of x is equal to integral x0 to x1 f of x comma y dash is defined on the curve y is equal to y of x. Graphically it can be represented as x-axis and y-axis. Take the 2 points. The curve y is equal to y of x in the extreme, y is equal to y of x is defined on the functional gamma of y of x is equal to integral x0 to x1 f of x comma y dash. That is, we only recurring that the admissible curves, we have the first order derivative. We can prove by a different method that the curve that achieves the extremum has a second derivative as well. Therefore take some admissible curve y is equal to y bar of x. Take some admissible curve y is equal to y bar of x. Here earlier we have seen that what is admissible curve. We know that admissible curve is a closed lying curve. Take some admissible curve y is equal to y bar of x close to y is equal to y of x and includes the curve y is equal to y of x and y is equal to y bar of x in one parameter, that is family of curves. We already discussed about family of curves. Therefore that is y of x comma alpha is equal to y of x plus alpha into y bar of x minus y of x. If alpha is substituting alpha is equal to 0 in the family of curves, we get that y of x is equal to y of x. If substituting alpha is equal to 1, we get that y is equal to y bar of x. Therefore since graphically it can be represented it as the admissible curve, that is close to close lying to the main curve y is equal to y of x, admissible curve y is equal to y bar of x. That is graphically it can be represented it as it. Therefore now we know the difference between, therefore we know the difference of y bar of x minus y of x is called the variation of the y of x. We know the difference, that is y bar of x, here y bar of x minus y of x of the way is called the variation of the function y of x. That is it is denoted by delta y. Say it as equation number 2. That is delta y is equal to y bar of x minus y of x. Then these function may be differentiated once or several times by the condition of a functional. Therefore the derivative of the variation is equal to the variation of the difference. What it means? That is the derivative of the functional, that is the derivative of the variation, that is d by dx of delta y. D by dx of delta y is equal to d by dx of y bar of it, where delta y, we know that delta y is equal to y bar of x minus y of x, y bar of x minus y of x. Therefore that is equal to here we get that y bar dash of x minus y dash of x, that is equal to, here we get that delta y dash, that is the variation, the derivative of the variation delta y, the derivative of the variation delta y whole dash is equal to the variation of the derivative, that is delta into y dash, that implies delta into dy by dx. That what it means, the derivative of the variation is equal to the variation of the derivative, delta y whole dash is equal to delta into y dash, that is delta into dy by dx. Simply we can write as delta y whole dash is equal to y bar of x minus y of x, which is equal to y bar dash of x minus y dash of x is equal to delta y dash. Therefore similarly delta y whole double dash is equal to y bar of x minus y of x whole double dash is equal to delta y second derivative. Therefore up to so on kth derivative, up to so on kth derivative, it can be written as the kth derivative of the variation is equal to variation of the kth derivative, delta y power of k derivative. Therefore we consider the family of the curve y is equal to y of x comma alpha. Therefore we consider the family of y is equal to y of x comma alpha, where y of x comma alpha is equal to y of x plus alpha into y of x comma alpha is equal to y of x plus alpha into delta y. Therefore for which alpha is equal to, for which alpha is equal to 0, here we get that for which alpha is equal to 0, here we get that y of x comma alpha is equal to, here what we have, y of x plus alpha into delta y. For which alpha is equal to 0, here we get that y of x is equal to y of x, and for which alpha is equal to 1, here we get that y of x is equal to y bar of x, that is admissible curve. Therefore if we consider the values of the functional, that is gamma of y of x is equal to integral x0 to x1 f of x comma y dash into dx only on the curves of the family. Therefore initially what we have initially what we have gamma of y of x. Gamma of y of x is equal to integral x0 to x1 f of x comma y dash into dx. Therefore transforming this equation into the family of into the curves of the family, y is equal to y of x comma alpha. Therefore then the functional equation 4 becomes, therefore gamma of y of x comma alpha then the functional is a function of alpha. Therefore gamma of y of x comma alpha is equal to phi of alpha. Say it as some equation 5. Therefore this function phi of alpha is extremizer for alpha is equal to 0. Since for alpha alpha is equal, since for alpha is equal to 0, we have y is equal to y of x. A necessary condition for alpha is equal to 0 is that the type of derivative for alpha is equal to 0 is vanish. Therefore that is pi, that is, it can be graphically, it can be represented it as pi dash of alpha at alpha is equal to 0, at alpha is equal to 0 is equal to 0. That implies pi dash of 0 is equal to 0. Therefore since gamma of y of x gamma alpha is equal to pi, so therefore from equation 5, therefore since from equation 5 gamma of y of x, since from equation 5 equation 4 becomes gamma of y of x comma alpha is equal to pi of alpha integral x0 to x1 f of x comma y of x comma alpha into y dash of x comma alpha into dx. Therefore since from 4 and 5, now differentiate above, equation 6 with respect to alpha on both sides. Therefore here we get, therefore equation 6 implies pi dash of alpha is equal to integral x0 to x1 fy into d by d, after integral it becomes partial derivative. Therefore dou by dou alpha into y of x comma alpha plus fy into dou by dou alpha into partial derivative of y dash of x comma alpha into dx. Therefore where here fy is equal to dou by partial derivative of f of x comma y of x comma alpha into and y dash of x comma alpha, and here fy dash is equal to dou by dou y dash of f of x comma y of x comma alpha into y dash of x comma alpha. That is, we are partially therefore here we are partially differentiating with respect to alpha, therefore since we written fy is equal to this and fy dash is equal to this. Therefore and also dou by dou dou by dou alpha of y of x comma alpha, partially differentiating dou by dou alpha into dou by dou y of dou by dou alpha into y of x comma alpha from equation 7. Since from equation 7 dou by dou alpha into y of x comma alpha is equal to dou by dou alpha into y of x plus alpha into delta y. Therefore partially differentiating with respect to y, alpha, y of x becomes equal to 0 and alpha into delta y with respect to alpha, partially derivative of alpha into delta y is equal to, here we get the delta y. Therefore here we get the delta y, and also similar, and also here partially derivative of y dash of x comma alpha, partially derivative of y of x comma alpha. Therefore here we get 0 plus 1 into delta y dash is equal to delta y dash. Therefore substituting 8 and 9 values in equation 7. Therefore the equation 7 becomes pi dash of alpha is equal to integral x0 to x1 fy, where in the place of partially derivative of alpha with respect to alpha y of x comma alpha. Here we get that delta into y, and here we get that delta into y dash. Therefore delta into y and delta into y dash. Therefore pi dash of alpha is equal to integral x0 to x1 fy into, and also here what is it is the variation, here what it is variation, that is delta y. We know that delta y is equal to y bar of x minus y of x is equal to derivative of y of x comma alpha, the value equal to delta y and delta y dash respectively. Therefore and also here we know that fy is equal to dou by dou y into f of x comma y of x comma alpha and y dash of x comma alpha, and if y dash is equal to dou by dou y dash into f of x comma y of x comma alpha and y dash of x comma alpha, say it as some a point, and a b point. Say using a point and b point and substituting 8 and 9 values in equation 7. Therefore here we get that pi dash of alpha is equal to integral x0 to x1 fy of x comma y of x comma alpha into y dash of x comma alpha into delta y, and fy dash is equal to x comma y of x comma alpha into y dash of x comma alpha into delta y dash into dx. Therefore since this equation from point A and point B, point A and point B. And therefore we know that the variation, therefore since we know that the variation of pi dash, since we know that the variation, that is here we already discussed, that is variation of pi dash of alpha at alpha is equal to 0, equivalent to is equivalent to 0, that is pi dash of alpha at alpha is equal to 0 is equivalent to 0. Therefore now therefore say it as equation number 11, and by here we are using these function pi dash of 0, where pi dash of 0 is called the variation of the functional, and variation of the functional and it is denoted by delta into gamma, therefore pi dash therefore denoting pi dash of 0 is equal to delta into gamma. Therefore the necessary condition, we already know that the necessary condition for an extremum of a functional gamma is that a variation that vanishes, that implies delta into gamma is equal to 0. Therefore for the functional gamma of y of x, integral x0 to x1 f of x comma y dash into dx. Therefore this condition from equation 10 implies, what is equation 10 here? Pi dash of alpha is equal to integral x0 to x1 fy into delta y plus fy dash into delta y into dx implies, equation 10 implies in the form of integral x0 to x1 fy into delta y into dx is equal to 0. We integrate the sum fy into delta y into dx. That is here clearly the equation 10 here clearly equation 10 becoming, what is equation 10 implies? What is equation 10 here? Pi dash of alpha is equal to integral x0 to x1 f of fy into delta y plus fy into delta y dash into dx, here taking, we know that the pi dash of alpha is equivalent to 0. Pi dash of alpha at alpha is equal to 0 is equivalent to 0, and also we know that the variation of the variation of the functional, and it is taking in the place of pi dash of alpha, that is pi dash of alpha is equal to delta into gamma, introducing the variation concept. Therefore the necessary condition for an extremum of a functional gamma is that a variation that vanishes, that implies here delta gamma is equal to 0. That implies clearly here we get that clearly here we get that delta into gamma is equal to integral x0 to x1 f of fy into delta y fy into delta y plus fy into delta y dash into dx. We know that the variation that vanishes, therefore it becomes, since delta into gamma is equal to 0, therefore the functional integral x0 to x1 fy delta y plus fy delta y dash into dx is equivalent to 0. Since earlier we discussed that that is gamma of y of x is equal to integral x0 to x1 f of x comma y of x comma y dash of x into dx is dx. And therefore earlier we have to we discussed that we have to equate the term gamma of y of x is equivalent to 0. Gamma of y of x is equivalent to 0. Since from this we are since here we are equating the functional equivalent to 0, that is integral x0 to x1 that is integral x0 to x1 fy into delta y plus fy dash fy into delta y dash into dx is equivalent to 0. Therefore we integrate here from the equation 13, Here from the equation 13, we integrate the second term. We integrate the second term by parts. Therefore, in taking integral x0 to x1 fy into delta y dash into dx is equal to, since here the concept is clear, that is that is after integrating here we get that fy dash into delta y into x0 to x1 minus integral x0 to x1 d by dx of fy dash into delta y into dx. That is the concept is delta y dash, the variation of the derivative of the variation is equal to the variation of the derivative, that implies delta into gamma. Therefore that implies saying this as delta into gamma, that is integral x0 to x1 fy into delta y, substituting in the equation 13, that is integral x0 to x1 fy into delta y into dx, plus in the place of fy into delta y dash, into delta y dash into dx, we are substituting these, we are substituting this fy dash into delta y into x0 to x1 and integral x0 to x1 d by dx of fy dash into delta y into dx. Therefore that implies fy dash. Therefore that implies writing these terms separately, fy dash into delta y x0 to x1 plus merging these two terms, integral x0 to x1 and minus integral x0 to x1 d by dx of fy dash into delta y into dx. Therefore taking integral common here, integral x0 to x1 here fy and minus d by dx of fy dash, minus d by dx of fy d by dx of fy dash, and take and also taking variation, and also taking variation delta y common outside. Therefore it is clear that therefore you get that integral, that is fy dash delta y into x0 to x1 plus integral x0 to x1 fy minus d by dx of fy dash into dy into variation of y into dx. It has some equation number 14. Therefore, but also we know that the variation at x is equal to x0, at variation x is equal to x0, that implies y bar of x0 minus y of x0 is equivalent to 0, since by the concept. Therefore delta y at x is equal to x1, y bar of x1 minus y of x1 is also equivalent to 0. Therefore, since the admissible curves in the problem passes through the fixed boundary points, earlier by the statement y of x0 is equal to y0 and y of x1 is equal to y1 are the bounded points which are satisfying the statement. Therefore, since the admissible curves in this problem passes through the fixed boundary points, then the variation delta gamma is equal to integral x0 to x1 fy minus d by dx of fy dash into delta y into dx. Therefore, the necessary condition for the extremum is in the variation is in the form of delta gamma is equal to 0. Since we know that delta gamma is equal to pi dash of alpha, where pi dash of alpha at alpha is equal to 0 is equivalent to 0. Therefore the variation that vanishes. Therefore that implies delta gamma is equal to 0. Therefore here we get that integral. Therefore here we get that integral x0 to x1 fy minus d by dx of fy dash delta y into dx is equal to 0. Therefore, from the said as some equation 15. Therefore, the first factor fy minus d by dx fy dash in 15 is continuous function. Therefore, by the second factor, delta y is an arbitrary function. The second function delta y is an arbitrary function. Therefore, second factor arbitrary is a function, therefore that satisfies only certain general conditions at x is equal to x0 and x is equal to x1. Therefore, by using the fundamental lemma of calculus of variation, by the fundamentals of calculus of variation, if for every continuous function eta of x, if for every continuous function eta of x, integral s0 to x1 pi of x eta of x dx is equal to 0, where the function pi of x is continuous, where the function pi of x is continuous and the interval x0 to x1, then pi of x is equivalent to 0, therefore is equivalent to 0 on that interval. Since all the conditions for the lemma, fundamental lemma of calculus of variation is fulfilled, therefore the function fy minus d by dx, fy dash is a continuous function and delta y is arbitrary. Therefore, hence from equation 15, fy minus d by dx of fy dash is equal to 0 on the curve y is equal to y of x, and which extremizes the functional under consideration, that is y is equal to y of x, is a solution of the second order differential equation. And fy minus d by dx, fy minus d by dx of fy dash is equal to 0. Therefore, this equation is called the Euler's equation. Therefore,